Okay, thank you very much for the presentation, for the opportunity to give this talk. It's a great pleasure to give a talk in this young audience, usually. I'll speak about advances in optical detection of magnetization. Actually, I like this topic because I will speak about connection between light, very simple entities, light and magnetism. As we know, this connection was first established by Michael Faraday, so it's a long story, but I'll make this story short. The most interesting stage of this research was started after advent of lasers into polarization measurement. So the plan of my my presentation looks like this. First of all, I'll say a few words just about basics of optical detection of magnetization. Then I'll speak about laser revolution in this field, and then about optical detection of magnetic resonance and optical detection of magnetic susceptibility, then about optical detection of magnetization fluctuations, and that's all. That's evolution of this research, I would say. So first of all, basics of this experimental research. These are very, very simple things. I think that everyone knows. Perhaps young people who are involved in magnetic measurements, perhaps they do not know so much about optics. And after all, as we used to say, повторение мать учения, right? So perhaps it will be useful for all of us. So in magnetic field, this is a simplest energy diagram of a paramagnetic ion, paramagnetic particle, paramagnetic atom in magnetic field, in longitudinal magnetic field. The energy levels are split in magnetic field so that position of absorption bands, of absorption lines change in magnetic field. So I can make, in principle, I can make a strong statement that in magnetic field, paramagnet changes its color. So in an exaggerated form, I can present it like this. We have some line which in magnetic field is split into two components. One is red, one is shifted to red, another is shifted to blue. And so the color is changed. If the paramagnet is magnetized, then for instance, this component, the absorption in this component is strong, whereas in this component is absent, for instance, then the paramagnet will be red. If we have magnetic inversion, for instance, the paramagnet will be blue, and so on. But like this, the picture like this can be realized somewhere, perhaps in neutron stars, or somewhere where the magnetic field is very, very strong. In reality, this splitting, of course, is much smaller, and we will be interested not in splitting, usually not in splitting of Zeeman components and corresponding splitting of dispersion tails of this spectra, but actually about difference in their intensity, because difference in intensity reflects difference in population of the ground state doublet, and actually it reflects magnetization of the medium. So by measuring the difference of absorption in two circular polarization in longitudinal direction, when we look along the magnetic field, we can measure magnetization. It's one way, and another way we can measure the difference between refractive indices for right and left circular polarized component. In other words, we can measure circular birefringence, which is responsible for Faraday rotation, as we know. So actually, when I started in the 60s and 70s, polarization magnetoptics was mainly used not to detect magnetization, but rather to study spectra of Faraday rotation, or MCD, magnetic circular dichroism, just to identify electronic transition and to extract Zeeman splitting for the case when this splitting is smaller than width of the components, when the Zeeman splitting cannot be resolved just spectroscopically. But still, at that time, there were some papers, some studies devoted to studying, to investigation of magnetization. I will give just one example. It's from my early work when I studied magnetic properties of rare earth ions in crystals. I have found that dysprosium ions reveals very, very long spin lattice relaxation times. This picture shows temperature dependence of spin lattice relaxation rate, and we can see that in the range of low of liquid helium temperatures and low magnetic fields, the relaxation times make some hundreds and thousand seconds, so very, very long. It was one discovery. It was absolutely unusual for earth ions. And another story is we just we measure behavior of magnetization of this ion after inversion of magnetic field. We did the following things. We first magnetized, we increased magnetic field until the values until the values corresponding to magnetic saturation, when population of the ground state became much larger than that of the excited, of the upper magnetic sublevel. And then we inverted magnetic field and observed what happens after this inversion. There are two possibilities. When this, as we know, when in zero magnetic field these sublevels experience just crossing, then the population of the lower sublevel will just become the population, so the crossing will not change population of sublevels. Another and more frequent situation occurs when there is some perturbation, some additional interaction which lifts degeneracy in zero magnetic field. This is a usual picture. And then the population will go like this. It's adiabatic passage, so to say, and then the situation will be different. In this case, we obtain inversion, population inversion, and here we have the usual positive spin temperature. And our measurements have shown that in this system, just a unique situation was realized when it's just several spectra of MCD of this system with the interval of about 2 minutes. The time goes down here, and we see that here it's already equilibrium MCD spectrum, and here it's MCD spectrum at the initial moment. So we see that that magnetization has different signs in these two situations, so that we achieved in this simple experiment, we achieved spin inversion, though the magnetic field was switched just by simple switch, so not so rapidly. Okay, it's just a small example of using optical means to measure magnetic spin dynamics in diluted paramagnet. But the main interesting stage of research in this field was related to advent of lasers into this system. When we, at the beginning of our research and in the 70s, we were thinking about achieving the greatest polarimetric sensitivity, the greatest sensitivity to small changes of polarization plane angle. And at that time, polarimetric sensitivity of the best polarimeters lied in the range of 10 to the minus 3 degrees. And it was considered something very high. But we estimated achievable sensitivity, have found that it should be at least 3 orders of magnitude higher. But why it wasn't achieved, it wasn't clear, though at that time lasers existed already for 10 years. Then we tried to achieve it and understood that the main reason why it wasn't achieved was that lasers, at that time at least, the fluctuations of their intensity were 3, 4, or 5 orders of magnitude higher than level of short noise. Short noise is a fundamental limit that limits polarimetric sensitivity. It's noise, it's quantum noise, or noise of photoelectrons in of photodetector. And so we just tried to solve this problem, and we have managed to do this. And the main thing we used for this purpose was a balance detector. It's a very simple thing. Now it's known to everyone, and it's manufactured commercially. This is a polarization beam splitter which splits the incident beam into 2 channels with 2 detectors. And in these 2 detectors, the behavior of the intensity as a function of the azimuth of the polarization angle of the incident light looks like this. And when the polarization angle makes 45 degrees with the polarizing direction of this beam splitter, the intensities in these 2 channels are the same, photocurrents are the same, they are subtracted here by this circuit, and so the output current is 0. And this 0 doesn't depend on intensity of the incident light, because intensity in both channels changes in a correlated way. But if polarization plane rotated by a small angle, then intensity in one photodetector increases, in another decreases, and the difference in the output of the scheme, we have double signal. So in this way we have managed to get rid of excess noise. At least we have managed to suppress excess noise by 3 orders of magnitude. It was enough to achieve short noise limited sensitivity. We also used some other methods. In particular, it can be useful for those who is involved in optical measurements. So we know that this is Malus Law, with dependence of intensity on the angle between polarization plane and polarizing direction of the polarizer. And it's usually considered that the most convenient, the most reasonable point for detecting polarization plane rotation is 45 degrees. 45 degrees, because of the steepness of this dependency is the highest in this point. But in reality, it's not the limit, because we can increase intensity of the light, then this Malus Law the sine squared will go somewhere higher above the ceiling, and then if we cross additionally the position of the analyzer, so to remain the photocurrent the same, we'll see that the steepness here will be high and the signal will be high. And so this is the method to increase polarimetric sensitivity, though it can be made efficiently with very high factor of gain, so to say, but until our sample can stand the intensity of the light, because the intensity of the light passing through the sample increases. And it was confirmed experimentally. Then there was another method, it's polarization pile method, which allows one to increase the angle of rotation, because if one component of the light is decreased, then for the small angle of rotation, which is shown here at the entrance into the polarization pile, at the exit, one component will be decreased, another will remain the same, and as a result, the polarization plane angle of rotation will be increased. It also allows one to increase sensitivity. Actually, it is important only when we have to fight against excess noise, in reality. It's useful. Then it's possible to use Fabry-Perot, as we know, Fabry-Perot cavity, where the Faraday rotation can be accumulated due to multipass of the light through the cavity. Okay. So as a result, the sensitivity was really increased by 3 or 4 orders of magnitude. It now lied in the range of 10 to the minus 8 or even radian or even better. And it opened a lot of new opportunities. So first of all, I'll say a few words about optical detection of magnetic resonance. In this audience, everyone knows what is magnetic resonance. We have some paramagnet in magnetic field, and we apply high frequency or microwave magnetic field to this sample. And when the frequency of this field or the energy of the quantum of this field coincides with magnetic splitting of the ground state, we observe magnetic resonance. Magnetic resonance can be observed in different ways. It can be detected just by measuring changes in the field, in this microwave field or high frequency field. It's one more or less conventional method of EPR detection. Another method or family of method, when we measure changes in the properties of this medium. For instance, it changes some optical properties or acoustic properties, or it can be heated or something like that. There are many methods of this kind. We are speaking about measuring Faraday rotation and measuring refraction index. And usually optical detection of EPR is performed like this. The microwave power is modulated at a frequency low compared with the spin lattice relaxation time, and when it is applied, the Faraday rotation decreases. When there is then in this gap, the Faraday rotation returns to its equilibrium state, and as a result, we obtain some resonance when the frequency of the applied field coincides with magnetic splitting, or it can be made even much more easier, just without modulating microwave field. The dependence of Faraday rotation on magnetic field and the presence of microwave pumping looks like this, and this is also was also used to detect magnetic resonance, but this can be used when we do not need high sensitivity. It's when the signal is huge. Okay, so it was applied in particular, I just give a few examples, in particular to detection of magnetic resonance of divalent thulium ion. It's a rare earth ion in low magnetic field. We have managed to go down to very, very low magnetic fields when the magnetic position of magnetic resonance became even lower than the width of the line. So it's some specific resonance. Anyway, it's just an illustration. Then it was found that rotation of transparent paramagnets, it was known before us, I think, but it was found then that rotation in particular of trivalent rare earth ions, which are transparent in the visible spectral range, so there are practically no transition, only very weak forbidden transitions. In spite of the fact that all the absorption bands are very far from the visible range in ultraviolet region, they show a pretty large rotation. We can see that their rotation, this is so-called diamagnetic rotation, so it's rotation without any impurity. And this is when the crystals are doped, are activated with different rare earth ions. We see that this paramagnetic rotation lies in the range of several degrees for the sample with a thickness of a couple of millimeters. Whereas the sensitivity of the polarimetric technique is 6 or 7 orders of magnitude higher. So it means that we can measure very, very small variation of magnetization. And on the base of this technique, we have measured, it's just example of EPR spectra of different rare earth ions, just randomly chosen from the series of ions. And we have found that practically all paramagnetic ions in dielectrics, in crystals and glasses, the spectra, EPR spectra, can be detected using this technique without changing the wavelength of the probe beam. So these measurements were made with helium-neon laser, and we didn't tune to any absorption, just it didn't matter. So the laser polarimetric technique was found to be convenient to detect EPR for all, practically for all transparent paramagnets. And on the basis of these results, we even have designed a laser magnetic spectrometer, which was manufactured by our Institute of Analytical Device Engineering, but it was only 2 pieces of this device were fabricated, and then perestroika has begun, and money was over, and this was forgotten. So now it doesn't exist. Okay, now about one more method. It's measuring magnetic susceptibility using this high sensitive polarimetric technique. It's a very simple idea. It was first, I think, used by Gorter, who, before the discovery of magnetic resonance, who measured magnetic susceptibility, but in parallel, in particular in parallel fields, but he did it on more or less concentrated paramagnets. We use strongly diluted paramagnets. The idea is very simple. We apply, along with the magnetic field, we apply an oscillating longitudinal magnetic field, and as shown here schematically, the magnetic splitting of the ground state will oscillate. If the frequency of this field is higher than spin lattice relaxation time, then practically no response will be detected, because the population will not follow the modulation of magnetic field. But if the frequency of this modulation is lower than spin lattice relaxation, right, then on the frequency of this modulation we will see modulation of magnetization. So, but by measuring the frequency dependence of the response of the Faraday rotation, we can measure spin lattice relaxation time. But it's not so interesting as another idea. If we, for instance, if we have more or less usual picture of behavior of levels in zero magnetic field or under some other conditions, we apply AC magnetic field with a frequency higher than spin lattice relaxation rate, then in large magnetic fields there will be no response, because population do not respond to this modulation. But in small magnetic field, in particular in zero magnetic field, we will see a response, because here the magnetization arises not due to changes in the population of the levels, but due to mixing of these two states, due to the fact that each of these state acquire magnetic moment when we change magnetic field. So this method allows to detect small non-diagonal, so to say, interaction, perturbation in the region of crossing or anti-crossing of levels. And this is the energy diagram of thulium ion. It's Breit-Rabi diagram, and we see that in this diagram, these two levels are split quadratically, first quadratically and then linearly, as it usually happens in these systems. And if we when we measured the modulation spectrum, spectrum of AC susceptibility, we see that there is Lorentzian curve, this one, which corresponds to hyperfine splitting, to this quadratic splitting I showed you. And there is one more peak, which corresponds to super hyperfine splitting due to effect of surrounding nuclei on this thulium ion. And there is one more peak which corresponds to point where the relaxation is facilitated due to crossing of the level that were shown on the previous picture, and with increasing concentration of ions, these peaks becomes more pronounced, and the number of these peaks increases. And for these measurements, the sensitivity to polarimetric sensitivity is very important, because it determines resolution of these pictures. Okay. Now it's one more example of modulation of spectrum of AC susceptibility of holmium ion in fluoride crystal, and also it shows how this method discovers structure of the ground state. Okay, now I'll speak about another idea. So all I spoke before, it was a more or less conventional method of research when you study response to applied perturbation, to applied magnetic field, AC or DC, and or microwave field, and so on. But we, in the beginning of 80s, we decided to measure, and actually to make this experiment, we invented the short noise limited polarimetric sensitivity. The idea was the following. So we know that dependence of any paramagnet magnetization on a magnetic field looks more or less like this. It's a Brillouin function, and for each magnetic field we have some definite value of magnetization. But if we look at any point of this picture more carefully through a magnifying glass, so to say, we will see that this magnetization is fluctuating. It's natural because the spins are moving, and as a result, magnetization of the spin ensemble consisted of finite number of spins fluctuates both in longitudinal and transverse direction, so that both the length and the direction of this vector fluctuate. So the question about whether it's possible to detect it or not depends, especially for macroscopic solids with a huge number of spins. It's the question of sensitivity. But the idea was the following. First of all, we thought about measuring longitudinal fluctuations of longitudinal magnetization. If the laser pulse passes through the medium in longitudinal direction with respect to magnetic field, then we expected that the noise will look like this, with a correlation time corresponding to the longitudinal relaxation time, to the T1 time, and the correlation function will be just exponential with the width corresponding to this time, and the spectrum will be Lorentzian with the width corresponding to this rate. But this idea, of course, is realizable, not very good, because we have to make measurements in the range of low frequencies where the different flicker noise are present, and so it's not very convenient from the experimental point of view. Another more interesting and more efficient way to observe this fluctuation is to direct the light beam across the applied magnetic field. Then any fluctuating magnetization directed along the light beam will precess around magnetic field during the dephasing time, during the time T2. Then it will be replaced by another realization. And so as a result, the fluctuations of Faraday rotation at the exit of the medium will look like this. The correlation function will have such an oscillatory shape, and the spectrum will be Lorentzian, centered at Larmor frequency with the width corresponding to the time T2, to the dephasing time. So in other words, what we have to observe in this experiment is just magnetic resonance spectrum of the system. Exactly this experiment we performed in 1981 with Evgeny Borisovich Alexandrov. Using as an object sodium vapor, we used dial laser, tunable dial laser. We tuned to one of the D line of the of sodium vapor and detected. I will not dwell upon details of this experiment, and we have managed to detect the signal with a signal-to-noise ratio of about 100. So actually there was no problem to detect the signal, but at that time we didn't consider it as an experiment, as a tool of research. It was just a sort of academic trick, as a sort of illustration to fluctuation dissipation theorem, perhaps. The more so that our estimates showed that, for instance, to apply it to paramagnet, to diluted paramagnet, more or less impossible. The sensitivity wouldn't be enough. Okay, and only nearly 25 years later, the first experiment on semiconductor was performed by Ostreich from Hanover, and these are the first signals that were recorded on gallium arsenide, and the accumulation time here was 6 or 8 hours. So it wasn't also a tool of research with such a sensitivity. But then a simple idea was proposed. Instead of using sweeping spectrum analyzer when we detect signal at one frequency at a time, it was proposed to digitize the signal and to use fast Fourier transform. To digitize with, it was possible to do it with a sampling rate of around of a few gigahertz. And then in real time, the Fourier transform was performed, and the spectra thus obtained were accumulated, and the sensitivity was increased by at least a couple of orders of magnitude. And after that, this method turned into an experimental, into a tool of research. These are just examples of our recording of signals at under different conditions of gallium arsenide. I just to illustrate the sensitivity. The signal-to-noise ratio here is sometimes around 1,000 or something like that. This is another example when we detected magnetic resonance in a single quantum well, 20 nanometer width, or width or thickness, as you like. So this quantum well was in a microcavity, so to increase the signal, and the signal-to-noise ratio here also is very high. So I just want to say what is the difference between method of magnetic resonance of conventional, so to say, of conventional magnetic resonance detection and magnetic resonance detection based on noise spectroscopy. In the first case, as it already was told, we use some additional field which excites the resonance. Here in noise spectroscopy, we do not excite the resonance. There is no source of high frequency or microwave excitation. We just switch on the field and just listen the system. We listen the system and we hear that it sounds at some frequency, at the frequency of magnetic resonance. If we change the magnetic field, the frequency of this sound increases or decreases, and we measure the spectrum of this sound, and this is magnetic resonance. So obtain all the information that is usually obtained from magnetic resonance. One more important advantage of this technique is that it is non-perturbative technique, because we do not perturb the system. We not only do not excite the magnetic resonance transition at the frequency of spin precession, but also the laser light doesn't induce any real optical transitions. So the system remains untouched, so to say. Then, of course, what's important that there is no generator, from the viewpoint of hardware. I'll show you. This is how looks the conventional spectrometer for optical detection of magnetic resonance, with all this hardware, with all this microwave stuff, and for comparison. And by the way, if we want to change the frequency range of the spectrometer, we have to replace all this hardware. It's a long story, but this is how looks spectrometer spin noise spectrometer. It's just laser light source, some polarizers and lenses, and sample in magnetic field, and detector and spectrum analyzer. Of course, this spectrum analyzer, it's just the brain or the heart of the system. It's a very complicated thing, but it's one piece of equipment, so to say. Okay. Now I'll speak about some properties of the spin noise spectroscopy which couldn't be predicted, actually, and which were discovered later, just for the last few years. First of all, perhaps you know that there exists a test, so-called Z-scan, which is intended to distinguish between optically linear medium and optically non-linear medium. It's very simple. The laser light beam is focused here, and the sample is drawn through the focal area of this optical system, and the transmitted light is detected. Then, if the sample is linear, there is no nonlinear effects, then we'll obtain just a straight line. Nothing will change, because there is nothing is changed. But if the properties of the sample depend on light power density, or in other words, if the sample is nonlinear, for instance, it experiences some self-induced transparency or bleaching, or some self-focusing or self-defocusing or something like that, then we'll see some peak or some dip in the center, which will reflect this nonlinearity. If we make such measurements with a regular magneto-optical signal, for instance, there is a coil and we modulate the Faraday rotation and detect it, then also we will not see anything while moving the sample over the focal area. But if we measure the noise fluctuations, if the noise, then we will see peak. And it's clear why it's so, because the main contribution is into the noise signal is made by the area of the light beam with the smallest diameter, where the number of spins is the smallest. There, the relative fluctuations are evidently the greatest. And so by moving this focal point over the sample, we can measure, we can monitor properties, special properties of the medium. And on the basis of this idea, there was realized 3D tomography. And the resolution along the light beam was obtained in the range of several microns. So it's it makes the spin noise spectroscopy from the optical point of view close to nonlinear optics. Another story also, which just reminds us about nonlinear optics, in spite of the fact that spin noise spectroscopy doesn't imply any nonlinearity in optics, any nonlinearity in optical susceptibility. If we we will measure dependence of spin noise as on the wavelength of the probe light. Let we have two components in optical spectrum, and we measure spectral dependence of spin noise. Then there may be two situations when these two components fluctuate independently, or they fluctuate in a correlated way. If they belong to the same spin system, then they will be correlated. If they belong to different spin systems, they will fluctuate independently. And depending on this, the spin noise signal will behave differently. It is especially, this is revealed in a especially pronounced way for the transitions homogeneously and homogeneously broadened. For instance, if we have in optical spectrum the band like this, with a Faraday rotation like this, and using linear optics, we cannot say anything about mechanism of its broadening. But if we measure spectral dependence of spin noise, we'll see that in one case, when the band is broadened homogeneously, we'll see a dip in the center of this band, so that in the point where the Faraday rotation turns into zero, the noise, the spin noise also vanishes, and it seems natural. But for inhomogeneously broadened width, we'll see that in the point where the Faraday rotation is zero, the noise of the Faraday rotation is the greatest, because there are many narrow components which fluctuate independently. And by measuring, and actually depending on the ratio between homogeneous and homogeneous width, the depth of this dip will be different and can be used to measure this ratio. One more example is that reminds us about nonlinear optics. We can using the spin noise spectroscopy, we can realize pump probe spectroscopy. For instance, if we illuminate some pump on the sample with one beam, and the question is, can we, using another beam, to find the point, the spot illuminated by this pump beam? Usual answer to this question is known. If the first beam changes optical properties in the area of illuminated spot, then we can do it. If it doesn't change, we cannot do it. But it's not the case for spin noise spectroscopy, because when these two spots will coincide, the fluctuations, the contribution to fluctuations from two beams will be correlated. When they do not overlap, they will be uncorrelated. And depending on this, it's clear that the total signal will be different. This was realized not in spatial, but in spectral domain, so to say, when the two lasers were used with slightly different wavelengths, and the object of study was ensemble of quantum dots. Then, when the wavelengths of these two lasers are different, then they probe different sub-ensembles of these quantum dots. But when they are the same to within homogeneous width of a single quantum dot, then the value of the noise signal changed. And as a result, they measured a very narrow, in this experiment, very narrow homogeneous width. And in conclusion, its example, okay, I'll skip it, I think. I just want to show you my favorite picture. It's, and it the more so that it has to do with nuclear relaxation. So these are spectra of spin noise of a semiconductor recorded. Each curve, it's a spectrum recorded one after another in approximately 1 second. And the system which is probed is gallium arsenide crystal that with the nuclear system preliminary optically oriented. So we first pumped it optically. Spins of nuclei in this system were oriented, and then we just measured the spin noise spectrum, and we see that the position of the peak of the resonance shifts gradually, drifts to its equilibrium position corresponding to zero, to equilibrium magnetization of nuclei. If we this is the same picture, but when the direction of nuclear polarization was inverted, then actually the field created by nuclei, so its Overhauser field was larger than the external magnetic field. So relaxation goes actually from here, but since we can measure only magnitude, only module of the field, it just reflects from zero. And so this picture, first of all, it shows nuclear relaxation, which can be studied in this way. But what's important for my narrative, so to say, is that the sensitivity of this noise spectroscopy, which seemed to be very low because for macroscopic bodies, because of huge number of spins, as we know, it appeared to be enough to detect for such short times, like one second of accumulation time, it's very short, with high sensitivity to detect small magnetic fields. So here the spin noise spectroscopy shows itself, reveals itself as a for magnetometry, so to say. And in conclusion, I want to say that now this spin noise spectroscopy is on the stage of its evolution, its development. It is clear that not all opportunities of this technique are already exhausted. And I think this is the story of optical detection of magnetization I wanted to tell you. Thank you very much for your attention.
First of all, I should thank you for your English language. It was very vivid, very fast. It even seemed to me that it was. Do you know Russian?
Sorry?
Do you know Russian language?
Yes, a bit. I tell you, повторение мать учения, remember?
It was. Even seemed to me that it was English, not American one. English. Do you understand?
Yeah, I understand. I can say that.
How many years you spent in England?
No, I know. I have been in the United States.
Yeah, in the United States.
Yes, but I can
one more question concerning your slides. One of the last slides were two color. Two color spin noise. What is that? Nature communications.
Nature Communications.
No.
There is such a journal.
See, look.
You see, my vision is very bad. I see it. Okay, I'm sorry.
Nature,
of course.
Thank you very much.
Там made, да. Там не nature, да. I'm sorry.
Thank you very much for this extremely interesting presentation. You mentioned as optical detection by EPR, yes? Did you estimate the number of spins in comparison to the usual EPR? It should be much less than the usual EPR because you have not the limitation due to the magnetic transition. And furthermore, did you also apply NMR via EPR detection in optical means? It means detect, you mentioned the example with the Oberhauser effect, but did you measure really NMR spectra via the electron systems in optical way?
We didn't detect NMR spectra. I know optically.
Yes, yes, optically, yes.
No, at least in these works we didn't do that, and I know that some, but after all, some things like the detection of a hyperfine structure, in some way it's detection of nuclei, but it's a little bit different. So
but it
we didn't do that.
Extreme gain in sensitivity if you have the optical detection, yes.
But you know that the light, polarized light, do not interact directly with spins anyway.
Yes, yes, yes.
And especially with nuclear spins, it's some. It should be, there should be some intermediate interaction that facilitates this interaction. So, as for sensitivity of optical detection of EPR, I can say that it strongly depends on a particular paramagnetic ion whose spectrum we detect. For instance, we made some special estimates just from this point of view, just to achieve some very impressive figures in terms of sensitivity to number of spins for divalent europium ion. It's a very interesting ion because the absorption, the allowed absorption is close to visible range, and there is a very, very narrow resonant line, and we can come very close to this line, and there will be so-called Macaluso-Carbino effect when we come to the resonance very closely, and the sensitivity will increase dramatically, and there we obtain some figures, very impressive, something like 100 spins or something like that. But it's very, very special thing. System.
May I have a second question, Mr. Chairman? You mentioned susceptibility measurements, and you referred to the work of Koda.
Yeah.
Did you also try to investigate the Shubnikov, the famous Shubnikov effect,
no.
nuclear susceptibility?
No, we didn't.
Okay, thank you.
Thank you.
Any more questions?
Very interesting talk. I just have two small questions because you did a laser assistant magnetic spectrometer. I just mean because the laser normally also heat the sample up. You know, the temperature will increase because I did some namely measurement about some frequency generation. It's also a IR technique. Also, it's two laser beam to measure the sample. I mean, how could you correct the temperature effect?
I can't say that I have caught the sense. You are speaking about measuring at different temperatures.
Yeah, no, I mean, that, if you use a laser to namely directly hit the sample, there will be some temperature jump. I think actually nanosecond or microsecond time interval. Or maybe I'm wrong.
I am sorry. Okay. Do we heat the sample?
Yeah, heat sample, yeah.
You know that the main amount of measurements were made, as I told, on transparent samples. So they nominally, the samples do not absorb the light. But of course, in reality, we have some problems with heating, because to increase the sensitivity, in some cases, we have to increase the light power passing through the sample, and we just should take into account and should be careful about it.
Okay. So the second, is there any application for the spin noise-based 3D tomography? Real case application.
It was only an academic experiment, I think.
Okay. Yeah. Thank you.
Any more questions?
No. Thank you very much again.
Thank you.